So my goal in this lecture is to present the generative process for LDA, the way of generating documents according to the model LDA, and then move on to non-negative matrix factorization, which is a more general technique for factorizing matrices, and discuss two algorithms for doing that are relevant to the same problems that LDA addresses, but are not equivalent to the algorithm that is used for LDA generally. So there are two essential ingredients to LDA and essentially any topic model. Again, there's a collection of distributions on words, which we call topics, and then we also have a distribution on topics for each document. So here I'm just giving another view of what I previously discussed, where if you imagine that we have these words constituting our vocabulary, so this is a toy example. In general, our vocabulary that we're going to use to model these documents will be thousands or tens of thousands of words, but now we're just focusing on these and saying this is the vocabulary that exists for this problem. Then if we show three different topics, for example, if we have up here 7 topics and we want to pick one, for example, the politics topic, and show the distribution on the words in the vocabulary according to this topic. If we call this the third topic, so we have a vector beta 3, which is a probability distribution on this set of words, then the high probable words would be things like vote, politics, power, and Senate, etc. We then focus on a different topic, for example, the sports topic. That will be represented by a probability distribution on exactly the same words, except its high probability words will be things like ball, score, and season, etc. And also with an additional topic, for example, a logic topic. And so each of these topics, and we could have many of them, is going to be characterized by probability distribution on the same exact set of vocabulary words, but they're going to have different probability distributions. Then what we have is for a particular document, we have a distribution on these topics. So for example, if one person sits down and writes a topic, what the model hypothesizes is that that person will pick a probability distribution on these topics. So we'll call that, for the first document, call that theta 1. And perhaps the highly probable words, the highly probable topics will be childhood and economics. And so most of the words picked for this document are going to come from these two probability distributions. And another person might want to write about something else, and a third person about a different topic, a different subject, which will be related through using words coming from these 4 different topics according to the proportion of the distribution on those topics. So the way that we represent a model like LDA, which is a Bayesian model, is the same as the way we represent any other Bayesian model, through a generative process. So we hypothesize a generative process for the data that we see, and then have to derive an inference algorithm for doing the inverse problem of learning the actual parameters or a posterior distribution on those parameters of the model that could explain the data that we saw. So for LDA, we have this generative process. We assume that we have k different topics underlying our data set, which means we have k different probability distributions on the same set of words. And each of these distributions should capture a theme by putting its probability mass on a coherent subset of the words. The prior model assumes that each of those topics is generated and independently and identically distributed as a Dirichlet distribution. So this is the prior distribution that's placed on each of the k topics. They're all generated, each topic is generated once by drawing from this distribution and then fixed for all time. Then for each document, so each individual document, we need to decide for that document how it's going to use the topics that are available to it. And so for the dth document, that is done by generating a k-dimensional probability distribution. So this is a distribution on the k different topics up here. So this is k-dimensional. It's a probability distribution that's generated IID from this Dirichlet distribution. And we do that once for each of the capital D documents in our data set. Now that we have for the Dth document a distribution on the different themes that beta captures, we have to generate the words that appear in that document. So that's done according to this third step. For the nth word in the Dth document, so this is, we're focusing on the Dth document and looking at the nth generated word, we first have to decide which topic that word is going to come from, and that's done by generating a topic indicator, call it CDN, from a discrete distribution using the distribution on topics for the Dth document. So CDN will pick out one of the capital K topics available to it, where the probability of picking a particular topic is encoded in this distribution vector theta D. Once it's picked out its topic, the actual word is finally then generated, and so this is the data level finally that we arrive at, where we actually see the data, the nth word in the Dth document, which is generated also from a discrete distribution where it uses the topic picked out by CDN. So C subscript DN is an index. It's a number between 1 and K that picks out the index of the topic to use to generate the data. And so that's why we're subscripting with CDN here, because this is going to now pick out the correct index for that word in that document. So a few things to notice. First, we don't know what any of these are except for the data X. We don't know what C is for each word in each document, so there are many of these indicators we have to learn. We don't know what the distributions on topics are, and we also don't know what the topics themselves are. So there are many different things we need to learn with this model. The other thing to notice is that this is what's called a bag of words model. So we're not modeling with LDA, we're not modeling language as it appears in order. We're simply taking all of the words that appear in the document and essentially throwing them in a bag and then jumbling them up and modeling the entire set of words without any reference to order. So notice that there's no order taken into consideration in this generative process. What this means is that if you actually tried to generate a document from this model, you would get nonsense. It's not going to make any linguistic sense. But it is good enough in practice to pick out the underlying themes in the document, the underlying topics, and also how that document uses those topics. So it's able to get the macroscopic view of what is the information that appears in this set of documents, but the modeling power is not fine enough to actually model language as it's used in the documents. So of course there are many of those models that have been developed to take care of those flaws or potential flaws, but we aren't going to discuss those in this course. Another question is what is going on with this Dirichlet distribution? So we haven't really discussed the Dirichlet distribution in this course. What a Dirichlet distribution is a probability distribution on vectors that are non-negative and sum to 1. So if we let beta k be a random variable generated from a Dirichlet distribution, what that means is that beta k is a vector of non-negative numbers that sum to 1. So we can view this as being a discrete probability distribution. So in that sense, the Dirichlet distribution is a probability distribution on discrete distributions. When we need to put a prior on a k or a v dimensional probability distribution, the Dirichlet is a natural choice. However, the Dirichlet itself is a continuous probability distribution. And so there are some of these things that can be a bit confusing that you need to think through about what all the moving parts are. Dirichlet distribution is a continuous distribution on what can be viewed as a discrete probability distribution. The other question is how the parameter of the Dirichlet distribution, what assumptions different values of this parameter are enforcing on the distribution. And so that's what I'm showing in the following few slides. For example, if we assume that the parameter to the Dirichlet is shared. So even though we have an index, we have a v-dimensional probability distribution in beta, and so we need a v-dimensional parameter vector in gamma. If we assume that all v values in that parameter vector are the same, we can then look at what different draws from this distribution will look like. So down here what I'm showing is a case where beta is a 10-dimensional vector, and so I have 10 different values in the x dimension here. And gamma is a vector of also 10 dimensions with the same value in each element. So I'm going to just say what that value is here. So gamma is a vector of 10 ones in this case. And then I generate 10 different random vectors from this distribution, and I will get something that looks like this. So these are 10 different random variables, all generated from a Dirichlet distribution with parameter gamma equal to 1. And so you can see that I get 10 different discrete probability distributions. They're all non-negative, and they'll all sum to 1. And they look something like this. Now, as I let gamma increase, you notice from 10 to 100, you notice that the random variables that I generate start to look more and more uniform. And so that's what the parameter does. It enforces a more and more uniform distribution as this parameter goes to infinity. And then if I go back in the other direction and let it drop from 1 down to 0, I get something that looks like this. I get more and more discrete distributions. So from 1 to 0.1 to 0.01, I'm sorry, not more discrete distributions. I get distributions that put most of its probability mass on a smaller and smaller subset of the dimensions. So in practice with Dirichlet, with latent Dirichlet allocation, these parameters will be set to something less than 1, which enforces our a priori belief that each topic should only put its probability mass on a small subset of the total number of words available to it. So for example, the sports topic would put all of its mass on the sports-related words, which should be a small fraction of the total number of words in the vocabulary. And similarly, for the prior distribution on the topic proportions is Dirichlet as well. And so if we let alpha be something that's less than 1, that enforces our a priori belief that each document only uses a subset of the different topics available to it. So if there are 30 different things a document could talk about, represented by 30 different topics, represented by 30 different probability vectors beta, we might set the prior alpha such that only 5, or on expectation only 5, for example, would be manifested in any individual document. But of course, because it's a random vector, we can have more or less than that number. And so we won't be able to discuss the actual inference algorithm in this course for latent Dirichlet allocation, because it uses something called, typically uses something called variational inference, which is not an inference technique that we'll be discussing. I do want to show an example of what LDA does learn on real data. In this case, a set of a few million documents from the New York Times over a 20-year period. And what I'm showing here is those 2 million documents were put into the LDA. We applied LDA to those documents. We learned the topics, and I'm showing 10 of those topics here. There were more in the model, but these are 10 of the topics that were learned. So each of these lists corresponds to 1 vector beta over, I believe, an 8,000 word vocabulary. So each of these lists has 8,000 words in it in principle, but we're only showing the 10 most probable words according to any individual beta. So if we call this beta 1, it's an 8,000 dimensional probability vector on the 8,000 vocabulary words, and these are the 10 most probable words according to that vocabulary, that vector beta 1. And similar, if we call this beta 2, beta 3, and beta 4, and so on, each of these represents 1 probability distribution on the same exact set of words, but the 10 most probable words changes based on which vector we look at. And you can do a quick scan to realize that each of these distributions is capturing a coherent theme or topic that could appear in these documents. And this is not something that's encoded in the model at all. This is something that's picked out in the posterior distribution because that information is contained in the data. And similarly, for every single document in the data set, we learned a probability distribution on these topics. So there would be more topics than just this, but for a particular document, we could have a probability of this topic appearing in that document, and this one, et cetera, et cetera. And that way we can compactly represent each document by a probability vector on the k different topics in the model, which says these are the themes that appear in this document, and also these are the themes that don't appear in this document according to that probability vector. I'm starting with LDA because it's a very popular and useful model for machine learning and with documents and also other discrete group data. So I want to cover it, but I'm covering it now because LDA is very closely related to matrix factorization. And so the way that we can see this is by asking for a particular document, what is the probability that the nth word in the dth document is equal to the index I. So we have a vocabulary list, and whichever word is indexed by I, that's what we're querying here, given only the set of topics and given only the distribution on those topics for the dth document. And so notice that there's no indicator here of which of the topics this word came from. C is gone. In other words, this is the marginal distribution where we've integrated out C, and so we'll write that here and see if we can calculate that. So here is the same probability we're asking for, and we write that as a sum over the joint distribution of the nth word in the dth document being equal to I, and the assignment of the nth word in the dth document to cluster or topic K. And now we have a joint distribution over this word index and also this topic assignment for that word. And now we sum out the topic assignment. And so of course we can, that's integral, or that sum is equal to the marginal distribution we're interested in. However, if we keep it this way, and then we break this down, this joint distribution over these two things, into a conditional distribution of x given c, and given beta, and of course because we have c, we don't need to know theta anymore, so x is conditionally independent of theta given c. That's why theta doesn't appear here. Then times the prior on the topic assignment given the vector theta. So I've broken this joint distribution into this likelihood times this prior on c. Then we can read off what each of these are given beta and given theta. The probability of a word, of the word I, given that that word comes from topic K, is just equal to the ith dimension of topic vector beta K. So we can read off the probability from beta given these two bits of information. And also the prior probability of any word in the dth document coming from topic K is just equal to the kth dimension of the dth probability vector theta d. So we have theta dk. And so we can replace these probabilities with these two values here. And now finally, let's let capital B be the matrix that we get. It's V for V vocabulary words by K for K topics. So it's a V by K matrix that we get by taking each of these topics and putting them along the column. One column is one topic. And let's also construct this matrix theta, capital theta, which is the K by D matrix that we get by taking each distribution on topics and putting them along a column. So theta D appears along the dth column, in the dth column of this matrix. Then we can also read off this probability by just taking this matrix product, B times theta, and getting all the probabilities for all words in all documents, and then reading off the idth entry, which is the probability of seeing word I in document D. And so we have this matrix product, and then we read off one entry. And so notice that, in a sense, topic modeling can be thought of as a non-negative matrix factorization. We want to learn a factorization of these non-negative matrix, of this matrix of non-negative probabilities, and we represent that as equal to a product of two matrices that also have non-negative values in it. So B and theta are both matrices in this case, and both have non-negative values in it. So we can view this, we can think of this as a non-negative matrix factorization problem.